Hello everyone. Welcome to today's lessons on polynomials. We will be discussing polynomial functions today. It is the next step after the last unit of quadratics. The vocabulary that we're going to be talking about today, some of we've already had, but we're going to be putting it together in ways that maybe we didn't see before. Degree and leading coefficient I went over last class, but I will be going over again in the lecture. End behavior will be new. Root zero we should already have from quadratics. The fundamental theorem of algebra we have talked about, and we should already know factors. Turning point and relative maxima and minimum will be today something new. So let's move forward. All right, so when we talk about a polynomial function, we're talking about something that has many terms, and x is raised to a power. So here we have three different polynomial functions. And who remembers how to determine the degree of a polynomial? Well, we look and we say, hey, which of the terms has the highest power? And in the first function, x cubed is the highest power. X is raised to the highest power of any of the terms. So we call that a third degree polynomial. In the second function, g of x, the term with the highest power is this one. So this is a fourth degree polynomial. And in h of x, the term with the highest degree or the highest power is the first term. So this is a seventh degree polynomial. So at this point, you should know how to find the degree of a polynomial. The other thing that we need going forward, and we did talk about this a little bit last class, is what is the leading coefficient? The leading coefficient is the number in front of x in the term with the highest power. So for example, in h of x here, this is the term with the highest power, and the coefficient is -2. The constant in front of the variable is -2. So we would say this has a leading coefficient of -2. Both f of x and g of x have a leading coefficient of 1. And we're not going to be so much concerned today with what the number is, merely whether that leading coefficient is positive or negative. So why don't you guys look at this problem and say, I want to know what is the degree and what is the leading coefficient of the following polynomial. The most common mistake is people look at the first term. But if you'll notice, this is the highest power. So it is a fourth degree polynomial. And the leading coefficient is -3. So it has a negative leading coefficient. Now the good news is they rarely will try and trick you like this, because most of the time they will write the polynomials terms with each term being in descending order of power. So the highest power first, the next highest power, and so forth and down the line. So most of the time the leading coefficient will be that first one, but you never know when they're going to try and get tricky on a test or an SOL. Our next topic we're going to discuss is end behavior of a function. And now might be a good time to remember domain and range. If you remember, domain is the input, and we generally refer to that with x's. And range is the output, and we can either use y or f of x. So the end behavior is saying, hey, as we put in, as x keeps getting bigger and bigger and bigger, what happens to the graph? So let's look at this line. As x gets bigger and bigger and bigger, what does the y do? Well, it goes up. On the other hand, as x gets smaller and smaller, what does the y do? It goes down. Over here on the second function, the quadratic, this parabola, as x gets bigger and bigger, the function gets bigger. But also as x gets smaller and smaller, the function still gets bigger. It goes up. And so in very simplistic terms, we would say the end behavior of the first function is that it's down, up, and the end behavior of the second function is that it is up, up. So for example, in this function, what we would say the end behavior is. Now, simply, we would say that this is up, down. How they're going to ask it to you on the SOL is, as f of x approaches infinity, x approaches negative infinity. That's this side. As f of x gets big, x gets smaller. And on the other side, we would say as f of x approaches negative infinity, because it's going down, x approaches infinity. X gets bigger and bigger. Now, as hopefully you discovered in the exploration, there is a pattern here, which is that if we have an even degree, 2, 4, 6, 8, if the degree of the function is even, then the end behavior is either up, up, or down, down. There's other things going on in the middle of the functions here, but right now we are just concerned with the end behavior. So if you have an even, it's up, up, or down, down. If you have an odd function, then they're going to finish in opposite directions. Either, and when we say odd, we're talking about first, third, fifth, seventh, ninth, so forth and so on. It's either going to be down, up, or up, down. And what's going to determine whether it's each one of these is what the leading coefficient is. The leading coefficient is positive. For an even, it's up, up. If the leading coefficient is negative, it's down, down. For the odd functions, if the leading coefficient is positive, it's down, up. And if the leading coefficient is negative, it's up, down. The easiest way to remember this really is to think about the simplest ones that we should know by heart in Algebra 2, which is the simplest even degree function is y equals x squared. Well, if a is positive, it's parabola up. If a is negative, it's parabola down. And all the even functions, while they have this other stuff going on in the middle, will share that exact same behavior. The simplest odd function we can think of is y equals x. We either have a line going up, or if we have negative slope, we have a line going down. And you will see that the end behavior here is the same as the end behavior we see here. Next up, we have roots. Now, as we learned in our quadratics unit, root is just another name for a real zero or x-intercept or solution when our equation is set equal to 0. So we look at a problem like, we look at this equation, and it has 1, 2, 3, 4 roots. Next up, we're going to have relative maximums and minimums, or as they like to refer to them on the SOL, turning points. Turning points is where the function goes from increasing to decreasing, or decreasing to increasing. Now that sounds a little confusing, but if I just circle the turning points here in green, we'll see it's pretty simple. Now they're called a relative maximum or minimum because this point is like is higher than all the other points around it. Right? If you're in a mountain range, you know when you may not be the tallest mountain in the range, but you know when you're at the top of the mountain. Right? Same thing, we know we're at the bottom of the valley. So this is a relative max. And this is a relative minimum. Both are known as turning points. Now, hopefully, we did our exploration and we're going to see some patterns emerge, which is if we have a standard first degree equation, right, which we generally write as y equals mx plus b, it's going to have at most 1, 0, and it's not going to have any turning points. And the graph is going to be a straight line. A second degree, well, we should know that, should still on the board from the quadratic equation, y equals ax squared plus bx plus c. And we know that when we draw the parabola, we can have as many as 2 zeros, and we're going to have one vertex, so that's one turning point. And the third degree equation is going to be y equals x cubed plus a whole bunch of stuff. And the graph is going to look kind of like this. And if you look, if we draw in an axis, we can see that this can have 3 zeros and 2 turning points. The fourth degree equation will often look kind of like a W. And if you look at it, even with this bobble in the middle, you still have the same end behavior that you did in the parabola. And this one can have 4 zeros and 3 turning points. And hopefully at this point we've figured out what's going on. Which is that we can have at most the same number of zeros. The number of zeros will always be the same as the degree. And the number of turning points is the degree minus 1. And so right away, without using the graphing calculator at all, we can get an idea of what the graph is going to look like. Now, once again, we have this chart was at the bottom of the exploration, so let's go over that. If we have an odd degree function and the positive leading coefficient, just draw a line. It's going to start at the bottom and go to the top. If we have a positive leading coefficient, think of the parabola. It's going to be up, up. And when the leading coefficient is negative, everything just flips. Now the correct notation is as f of x, which is the graph, goes down to negative infinity, x approaches negative infinity. And as f of x approaches positive infinity, x approaches infinity. Now, personally, I like to think of the x's first and then go back. As x gets big, y gets big. As x gets small, y gets small. But for some reason on the SOL, they always write it with the f of x first. So that's what you need to get used to looking at. So for this one, as f of x approaches infinity, x approaches negative infinity. And that's this one. But we also have, as f of x approaches infinity, x approaches infinity as well, which is that one. So just think, as the graph goes up, the x's go down, and as the graph goes up on the other side, the x's go up. These would be the same, just reversed. These two over here. So, let's talk a little bit about what we would do here. Can we figure out, I gotta find a place to hide that. Can we figure out which one of these graphs goes where? So let's start with the ones we know. That's a straight line, so, and it's going up, so we would say that's going to be y equals x. How about this one then? Where would this go? Well, it's a straight line, so it's going to go, but it's negative, so it's going to go there. Next easiest one would be this one. We should know by now that that's a parabola, and because a is positive, it's going to be a parabola up. Now it's starting to get a little tricky. Let's look at this one right here. It's a fifth degree, so that means the end behavior is going to be opposite. One end is going to go down, and one end is going to go up. The leading coefficient is positive, so it's going to once again be like the y equals x. It's going to start down and end up. And the last thing we know is that it's going to have 4 turning points and as many as 5 zeros. And in this case, this has 1, 2, 3, 4 turning points, so that must be the x to the 5th. So if that's the x to the 5th, then this one must go up here with the one that has 1, 2, 3, 4 turning points as well. And now, based on this, we can figure out the other ones. This x to the 4th is going to have the same end behavior as the parabola, which is up, up. So it must be that one. And this one has the same end behavior as a parabola that's down, so it must be this one. The last two are a little bit trickier, and what we're going to find is that this one goes here, and this is going to be x cubed plus some other stuff. But if we look at the pure function y equals x cubed, we get a weird point here in the middle where it's a turning point and a 0 at the same place. And we'll see that here as well, and we'll learn probably next class about that because it's what's known as a double 0. So what we learned a few minutes ago about the relationship between the degree of the function and the number of zeros is summarized by the fundamental theorem of algebra. And, officially what it says is for every non-zero single variable polynomial with complex coefficients has exactly as many complex roots as its degree. Basically, it says this. If you have a 5th degree polynomial, there will be 5 zeros. Now, the key thing is that they do not always have to be real. they can be complex, meaning they contain I. The one thing you should know is that complex roots always come in pairs. So you can have 3 real and 2 complex roots in a 5th degree equation, or 1 real and 4 complex roots. In a 4th degree equation, you can have 4 real zeros or 2 real zeros and 2 complex zeros, but the sum of the zeros is always going to add up to the degree of the function. Okay, the last thing we're going to talk about is the relationship between roots, factors, and zeros. So let's look at this fairly simple quadratic. And if I ask you to factor this, we should be able to very quickly see, hey, what are 2 numbers that multiply together to give me negative 12 that add up to 1? And hopefully at this point, we wouldn't have any trouble figuring out that's x plus 4 times x minus 3. Now, if you were to graph this equation, what you would notice is that you would see zeros at negative 4 and 3. Feel free to do it on your calculator. And what you will see is that there's always a relationship between the zeros and the factors. And we've seen that a lot in the quadratic unit, and that same concept pushes forward into the polynomial unit. So, for example, if we look at this equation, this polynomial function, we will see that there are zeros at 0, negative 3, and negative 4, which means that the factors have to be x plus 4, x plus 3, and x. And sure enough, if we were to FOIL this all the way out, that would be x squared plus 4x plus 3x plus 12 all times x, or x squared plus 7x plus 12 all times x, or x cubed plus 7x squared plus 12x. So if we know the factors, we can figure out the zeros, and if we know the zeros, we can figure out the factors. The only place where this gets a little tricky is problems like this one right here. Because if we look at it, we see that it only has 2 real zeros, one at negative 1 and one at 1. But it's a 4th degree equation, which means it has to have 4 roots. So where are the other 2 roots? Well, remember, a 0 is when the equation is set equal to 0. Now, if we're on our toes, we will notice that this is a difference of squares. This is x squared minus 1 times x squared plus 1. And if we're really on our toes, we notice that the first term here is also a difference of squares, so that can be factored as x plus 1 and x minus 1. But we cannot factor a sum of squares. So if we solve, the zero product property says that any 2 numbers or any numbers multiplied together to give you 0, one of the numbers must be 0. So either x plus 1 equals 0, in which case x equals negative 1, or x minus 1 equals 0, in which case x equals 1. And those are the 2 real zeros that we're seeing over here on the graph. But the last one's a little tricky. How do we solve x squared plus 1 equals 0? Well, we would subtract 1 from both sides, and we get x squared equals negative 1. And then we take the square root of both sides, and one side would become plus or minus, and the square root of negative 1 is defined as I. And those are my other two roots. So my roots are negative 1, 1, negative I, and I. And so we end up with all four zeros, just two of them are imaginary. As I said earlier, one of the useful tricks to remember is that imaginary roots always come in pairs. So you would never have one imaginary root. You will always have two or four. So let's look at one last example here. This is clearly an odd function. There are two turning points, but there's only two real zeros. Now, our natural reaction is, well, the other zero must be imaginary. But as we just said, imaginary zeros always come in pairs. So where is the other zero? And what we want to notice is that this point here is a turning point and a zero. Excuse the interruption. And if we factor this, we will see this. This is easy enough to factor. All right, so we set it equal to 0 to find the zeros. And then we're going to solve it by factoring. Well, it's easy enough to factor out an x. And then the second part is easy enough to factor as x plus 1 times x plus 1. And so our zeros are 0, negative 1, and negative 1. And so this is what's known as a double zero. And whenever you have a point that is a turning point and a zero, a relative maximum on the axis, that's going to be what's known as a double zero. And the zero is appearing twice, which is why it only has the two zeros. It's really three, it's just that this one counts twice. Whoops, let's spell twice. Okay, so let's put it all together and see if we can't graph a function. So first of all, when it's factored out like this, sometimes it's difficult to figure out the degree. So the number of factors is going to be the number of degrees. So here it's 1, 2, 3, 4 factors. So this is going to be a fourth degree equation. The leading coefficient is negative, which means that the end behavior is going to be down, down. Our zeros are 0, negative 2, positive 1, and positive 3. So it's going to come up and kind of do that. And notice I didn't find any other points. If we really wanted to make the graph truly accurate, we would find more things. But in this unit, we're just trying to get a rough estimate of what the graph would look like. And here is a better picture of it. And I didn't make my loops big enough, but the general shape is still there. So if we have the factors, we should be able to plot the zeros and get the general shape of the graph once we know the end behavior. So let's look at this problem. Is it odd or even degrees? Well, it starts down and ends up, so it's clearly odd. Where are the zeros? Well, there's a 0 at negative 2, a 0 at 0, and a 0 at 1. And what is the end behavior? Down, up. Or, in official, as f of x approaches negative infinity, x approaches negative infinity, and as f of x approaches infinity, x approaches infinity. And like I said, most of the time when we think about this, we think about the x's and what comes out of the y. But for reasons unbeknownst to us, this is the way they're writing it on the SOL. So let's look at this. It says, describe the end behavior, determine whether it represents an odd or an even function, and the number of real zeros. So here on this first one are the axes. So end behavior is up, up, meaning that it's an even function. And there are 2 real zeros. Now the last part is guess the degree of the function. Well, there are 1, 2, 3 turning points. So I'm going to guess 4th degree. For this next one, there's 1 0. There is end behavior is up, up, so it's even. And since there's only 1 turning point, and that looks a whole lot like a parabola to me, I'm going to guess 2nd degree. All right, number 19. The end behavior is down, up, so that's clearly odd. There are 1, 2, 3, 4, 5 zeros. There are 1, 2, 3, 4 turning points. So I'm going to guess 5th degree. This here is a straight line. The end behavior is down, up, so it's odd. And since there are no turning points, I'm going to go ahead and say that that's a 1st degree equation, because that's what a line is. This one is down, down, so that's even. Obviously, the leading coefficient would be negative. There are 1, 2, 3, 4 real zeros. So I'm going to guess 4th degree. This last one here has end behavior is up, down, so that's obviously odd. Leading coefficient's negative. There are 1, 2, 3 zeros, but there are 1, 2, 3, 4 turning points. So I'm going to guess 5th degree. And what we see up here is that this little wiggle that never crosses the x-axis is a pair of imaginary zeros. The last thing here is intervals over which x is increasing or decreasing. Increasing is easy. As you go left to right, where is it going up? Well, it's going up from here to here. So the interval is from negative infinity up to, now it's asking intervals of x, so up to 2. And it's decreasing from 2 to infinity. And this is the part that confuses people, is they're like, well, it's going down, so why is it infinity? But it's asking what values of x. And so if we look, the function is decreasing over these values of x. And so that's 2 to infinity. All right. I hope that answers everything that you need on the worksheet. Once again, by now we should know all of these. We should have degree, leading coefficient, end behavior, root 0, the fundamental theorem of algebra, which is really scary sounding, but not that big a deal. Factors, turning points, relative maximum, relative minimums. The worksheet should be being passed out, or you should already have them. And if you have any questions, ask Mr. Dillard. I'll see you guys on Monday.